Uh, well, good afternoon, friends, students, friends of BSc 4th Sem. I'm continuing my discussion on electromagnetic theory. In first part, we had some mathematical background like gradient of a scalar, divergence of a vector and curl of a vector. In addition to this, there are other tools. We have discussed what is called as line integral, surface integral and volume integral. In addition to these tools we have in vector calculus or vector analysis, we have some theorems in electromagnetic theory. As far as our syllabus is concerned, or there be theorem in vector calculus. Hope you are going to study this in detail in mathematics in vector calculus. Still, we need here and we are discussing them. We have three theorems without any proof. What is called as Gauss divergence theorem, Stokes theorem and Green's theorem. In fact, Gauss and Stokes theorem, Green's theorem is a corollary of Gauss divergence theorem. Well, already I have written both the statement in words as well as mathematical statement on the whiteboard here. So Green's Gauss theorem, Gauss divergence theorem. This Gauss divergence theorem help us in transforming, say, a volume integral to surface integral, or we can convert a surface integral into volume integral. So here, that is the basic idea of this theorem. Whenever we need a conversion of a surface integral to volume integral, or vice versa, volume integral to surface integral. So we can make use of this theorem and we are going to make use of them shortly. This theorem states that the surface integral of the normal component of a vector A, the surface integral of the normal component of vector A, that means we have been given a vector field and in that a vector A, and we have found its normal component, that is A dot ds over the surface taken over a closed surface. So the first part of the statement is this: the surface integral of the normal component of vector A over a closed surface S is equal to the volume integral of the divergence of the vector A. Divergence of vector A taken over the volume enclosed by this surface. Yes, I repeat, the surface integral of the normal component of a vector A or a closed surface S is equal to the volume integral of the divergence of the vector A taken over the volume B enclosed by the surface. This means any surface is given to us. In this surface, yes, encloses a volume V. So the surface integral is transformed into volume integral. This theorem helps us in transforming a volume integral to a surface integral. In other words, we can say converting a triple integral into double integral or double integral into triple integral. So this is the tool which we have added according to our syllabus, which we have added to the pool of knowledge here. So the idea behind this theorem is convert a double integral into surface integral or surface, say, triple integral into double or surface integral into volume or volume to surface. The idea behind this. No proof is required here. There is a lengthy proof and it is given. If you want, you can find any book on vector calculus or mathematical physics, and that they have mentioned its proof. Okay, let's go for Stokes theorem here. It's another theorem. Now, I have written its mathematical statement. Here, the line integral of vector A taken around a closed curve which bounds the surface S. A curve, say any closed curve here, which bounds a surface S. Line integral of vector A around a closed curve which bounds the surface S is equal to the surface integral of the curve of a vector A taken over the surface S. In simple words, here this theorem known as Stokes theorem help us in converting a line integral, maybe closed line integral or a line integral, into a surface integral with this curve of a vector. Whenever we are taking a vector A and we are finding, say, the line integral of that vector A around a closed curve which bounds the surface S, which equals the surface integral of the curl of a vector. This is given vector. Here we are finding curl of a vector. We can show by proving its LHS is equal to RHS or RHS is equal to LHS. This theorem helps us in converting single integral into double integral or double integral into single. Vice versa is true in this theorem as well as in this theorem. Well, as I mentioned earlier, we have to discuss some mathematical background, and for that we have discussed gradient of a scalar, divergence of a vector, curl of a vector and their physical significance. We have discussed it at length. We have learned about line integral, surface integral and volume integral. Those surface, line, volume, divergence, gradient and curl we are using in this theorem. That means we convert a volume integral into surface integral or triple integral into double integral using Gauss divergence theorem. Here, using Stokes theorem, a double integral or a surface integral is converted into a line integral, or line integral is converted into double integral. This Stokes theorem helps us in transforming a line integral of vector into a surface integral of curl of a vector. This is important. Here this is important. So these two theorems. We have another theorem mentioned in our syllabus, which is known as Green's theorem. In fact, Green's theorem is again a corollary of Gauss theorem. I have mentioned just now that volume integral or a triple integral is converted into surface integral with this. Okay, look at the statement here, mathematical statement. This is surface integral. This is surface integral. Double integral is surface integral. You need not write it. With summation, I will explain that. Into a volume integral. Into a volume integral. This theorem has been explained for different cases, and those cases are nothing but, say, Green's theorem here. So to explain the statements, not the proof, explain the statement, what we are doing here, we are taking, say, I have written here, if u, v, w are some continuous function of Cartesian coordinate x, y, z, then we have written summation of double integral L u m v n w ds, which is equal to negative, that is volume integral, okay, dou u by dou x plus dou v by dou y and plus dou w by dou z dx dy dz. This is nothing but volume, and this is nothing but three-dimensional space vector, you can say. Now, point here is the summation sign indicates that we are summing the surface integral of different bodies here. We have summed the surface integrals of different bodies, and then if this summation indicates summation of integrals of different bodies, and that is converted into a volume integral. Okay, this theorem enables us to express, that is, integrals taken over the surfaces, different surfaces of number of bodies, as I mentioned, different bodies, as an integral through the space between them. This is the space equation here. This is one, and this statement belongs to a Cartesian statement or Green's theorem statement in a plane. In a plane. Statement in a plane. Another statement of this theorem, we can say this Green's theorem is important corollary of Gauss divergence theorem. Let's say phi and del. Phi and psi. Here, phi and psi are two continuous scalar functions, and they have continuous derivatives. Continuous scalar function or any scalar function having continuous derivative, that is phi and psi. In that case, we can write the volume integral of those two continuous scalar functions and their derivative. This is volume integral, which is equal to the surface integral, where n is an unit normal or outward normal drawn over the surface n. This is. So these are certain theorems. Sometimes they ask these theorems for 2 marks. Please prepare these theorems. If they ask, you do answer that. Let's go for the important important part of this electromagnetic theory or heart of the electromagnetic theory of your syllabus, that is Maxwell's equations. So mathematical background which we supposed to study and require here to discuss this mighty Maxwell's equation, which we have discussed now. That is first part of your syllabus. Now the second part is Maxwell's equation. Maxwell's equation we can derive in differential form as well as in integral form. For our syllabus, derivation of Maxwell's equation and its differential form is mentioned, and we are also discussing integral form of these Maxwell's equation and their physical meaning. Well, this happens to be second part of this topic, and then we have some application like writing the general wave equation for electromagnetic wave equation, plane wave equation, and Poynting vector, and transverse nature of electromagnetic wave equation. We are restricting ourselves to the syllabus. There are many. See this point to be remembered. Why this equation I have been calling them as a mighty equations? Why? The reason for this, today we are using in our day-to-day life the application of these equations, and that is nothing but communication. So technology has been developed in a fast and in such a beautiful way, so that we are using the technology in our pocket, that is a mobile. See, this electromagnetic wave is a carrier of energy. It carries the energy and we call it as a signal. So signal in the form of, say, video signal, audio signal, both video and audio, and we are making use of this. There are many things involved, but it could be possible because of these four equations. Well, these four equations may be obtained or studied in different mediums, different medium or media here. What do you mean by medium? It's not that say soft media or hard media like paper and this. It is, see, these four equations are known as Maxwell's equation. We'll discuss them one by one. These equations can be obtained or can be derived, can be studied in vacuum. These equations can be studied in material medium. And for our syllabus, we are discussing these equations in material medium. They are widely used in communication. You take any sort of communication, whether it is analog communication, whether it is digital communication, any sort of communication. So, transferring a signal from one place to another place in the form of electromagnetic wave, and that electromagnetic wave is nothing but it's due to these equations. Okay, so Maxwell has tried to obtain this equation. Maxwell has done wonderful work saying these are electromagnetic wave equation. We have studied this equation in our regular syllabus like electricity, electrostatics, magnetism or magnetostatics and so on. But he has clubbed them and he has applied for, say, for a communication. Many people, not only Maxwell, but he is the main person to write this wave equations. Now here we are calling them as Maxwell's equation. Let's introduce ourselves. What are these Maxwell's equation in their differential forms? There are four equations of Maxwell. I have written them. One is this, that is del dot D is equal to rho. And this equation is the result of, equation number 1 is the result of Gauss theorem in electrostatics. We have studied this, nothing new for it, but the way he applies to the electromagnetic theory is a wonderful result here, and today it is possible because of this Maxwell's equations. In this, it is resultant of a result of Gauss theorem in electrostatics. Here, rho is the density of charge. Rho is the density or charge density, and D will just get acquainted with this equation. We have discussed this. This is nothing but electric displacement current or electric displacement current. Or normally we call it as electric displacement. Fine. So we need not worry about the units and other things. The equation number 1, that is del dot D, D is a vector, that is electric displacement, is equal to charge density rho. It's due to Gauss theorem in electrostatics. He has named it as equation number 1. That is Maxwell's equation number 1 of electromagnetic theory. Hope you got this. Let us go for this del dot B. And this del dot B is the application of Gauss theorem to magnetic field. This equation is the application of Gauss theorem in electric field. This second equation is the application of Gauss theorem in magnetic field or magnetostatics. We call here it as electrostatics, we call here it as magnetostatics. This forms the Maxwell's second equation. You may wonder why the already applied equation is called as Maxwell's equation, because this equation have been or applied or studied in different media like vacuum, say material medium, or even dielectric medium, and so on. And see, the signal which is transmitted reaches to us in the form of mobile or any other form is in the form of electromagnetic wave. And that electromagnetic wave or its theory and its propagation or its communication part is understood theoretically using the set of equations known as Maxwell's equation of electromagnetic theory. Well, in this it is result of Gauss theorem or application of Gauss theorem in magnetic field, in which B is magnetic induction. Magnetic induction. We have studied what is the magnetic induction, what is electric displacement current. Last semester we have studied more about this. And in magnetics or effect of magnetism on current, you have studied this. Nothing new for us. Now, the equation number 3, that is We have studied electromagnetic induction EMI in PU second year. We have studied the Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction EMI and Lenz's law. Faraday's laws and Lenz's law we have studied in electromagnetic induction. Here B is magnetic induction, E is electric field intensity. E is electric field intensity. B is magnetic induction, B is a current density, it is electric displacement vector, which we have studied last year when we have studied dielectric theory last semester. This is based on this equation. Equation number 3 is the application of Faraday's law of electromagnetic induction and the Lenz's law, which gives the direction of induced EMF. Well, what about this equation number 4? Equation number 4, it is result of Maxwell. We have studied Ampere's circuital law in third semester, and we have applied that Ampere circuital law. Fine. For a magnetic field accompanying electric current, we have applied Ampere's circuital law for magnetic field accompanying electric current. Here H is say magnetic field intensity. Magnetic field intensity. We are getting acquainted with these equations, information about this. H is magnetic field intensity, J is, this is electric displacement vector D, J is current density. Current density. We have studied about Ohm's law, or else if you go through any book on electricity, magnetism, and if you explain electromagnetic waves, they explain about this electric displacement current density, magnetic induction, electric field intensity, and magnetic field intensity. This is current density, a vector quantity. This is electric displacement vector or electric displacement current D. This equation number 4 or fourth equation of Maxwell's equation is a result of, that is, Maxwell has modified Ampere circuital law. Ampere circuital law. Basically, Ampere circuital law is applicable only for steady current. For a changing electric field which gives the changing magnetic field, this was not applicable. And what is this? This is nothing but J plus this factor. That is, again, it will have the variation of electric displacement current, that is nothing but time variation of electric displacement current, will have the dimension of J, the current density. This is a brief information regarding, called as Maxwell's electromagnetic equations or Maxwell's equation. Let us go for derivation of these equations one by one, and this is core part of your syllabus. This derivation, though they are simple both say meaningfully as well as you can do it mathematically, because a sufficient background we have now. We have the different theorems, we have the line integral, surface, volume, curve, we know what is meant by curl of a vector, we know what is meant by divergence of vector and gradient of a vector. So let us go for equation number 1, that is del dot D is equal to rho r. It is written as, say, divergence of D is equal to rho, the charge density. For this, to derive this equation, let us consider a surface. Consider a surface bounded by value. Imagine we are in this hall, right? It is value, and this is a surface. Board is a surface. Consider a surface. Let us consider a surface bounded by volume V. Yes, this board is a surface here, and that too, consider a surface bounded by volume V in a dielectric medium. Dielectric medium. We have studied in third semester lot about dielectric medium and theory of dielectric medium. There we have come across what is called as polarization, electric polarization. We know in dielectric medium there are two kinds of charges. Two kinds of charges. What is known as free charges and say polarized charges or induced charges. Induced charges. When we have two kind of charges in dielectric, we have two kind of charge densities. Say rho is the charge density in dielectric medium due to free charges. And let me write rho p is the charge density of polarized charges. Charge density of polarized charges or induced charges. Let rho and rho p be the charge density, say density of free charges and the density of polarized charges respectively.